Hi, my name is Kingsley Azar, and this is my presentation on my report, Resource Utilization and Economic Efficiency in Remote Northern Ontario, Techno-Economic Analysis. This is my introduction. So basically I chose Sudbury as the town for my case study further down in the report. An overview on Sudbury. Sudbury is a major mining hub in Ontario, Canada, known for its extensive nickel and copper deposits. The region has a long history of mining activities, making it a critical area for studying resource extraction practices. However, the region faces challenges related to environmental sustainability, community well-being, and economic efficiency. And the objectives of this study was to explore how advanced technologies can help balance these competing demands by enhancing resource extraction processes. Scope of the study. So I performed a cost-benefit analysis, an environmental impact simulation, resource extraction process simulation, renewable energy integration simulation, transportation network simulation, water and waste management simulation. And I used MATLAB for all these simulations. Cost-benefit analysis. So the cost of implementing advanced technologies and infrastructure upgrades against projected benefits were compared over a defined period. These were the input parameters I used for my analysis. The initial investment was 50 million Canadian dollars. The annual operating cost was 5 million. Expected annual revenue was 100 million. The project's lifespan was 20 years and a discount rate of 5%. So this is a chart for my cash flow calculations. Cash flow is that would be the annual expected revenue minus the annual operating costs, and PV, which is the present value of cash flow, was calculated as the cash flow multiplied by the discount factor, and I found the discount factor is the mathematical equation for that is 1 over 1 plus the discount rate to the power of the year in which you calculated for. This net present value calculation, the NPV, that is calculated by summing up the total present value from the previous table and subtracting the initial investment from that to get this value right here. And I also I conducted a sensitivity analysis to evaluate the impact of varying discount rates on the NPV in the table right here. And the analysis of this revealed that even with a higher discount rate of 7%, the NPV remains positive, indicating the robustness of the project's economic viability under different financial conditions. So the cost-benefit analysis for Sudbury's advanced resource extraction technologies indicates that while investments are high, the long-term benefits significantly outweigh the costs. Economically, the analysis reveals reduced operational costs, increased efficiency, and enhanced profitability due to lower fuel consumption and maintenance. And also environmentally, the adoption of advanced technologies leads to substantial reductions in carbon dioxide emissions, improved water quality, and better regulatory compliance. Socially, the initiatives to create jobs, enhance community infrastructure and quality of life, and strengthen community relations. Overall, the analysis demonstrates a favorable return on investment and underscores the importance of sustainable development for economic efficiency, environmental protection, and community well-being. So the environmental impact simulations. To illustrate an environmental impact simulation for a techno-economic analysis in Sudbury, can focus on assessing the potential impacts of various scenarios involving resource extraction and the implementation of sustainable practices. So for these simulations, there were three separate simulations that I performed. It's a air quality simulation, a water quality simulation, and a land degradation and reclamation simulation. So this is for the air quality simulation. Annual emissions of sulfur dioxide, NOx, and then particulate matter PM 2.5 from local mining operations are 50,000 kilograms, 30,000 kilograms, and 10,000 kilograms per year, respectively. And all these values are assumed for this simulation in particular. And also meteorological data, including an average wind speed of 4 meters per second, an average temperature of 10 degrees Celsius, and 70% humidity. So, using MATLAB, a Gaussian dispersion model was developed to simulate the spread of these pollutants. So, after the simulation, this is the results I got for the graph. This is a the Gaussian dispersion model used to simulate the spread of the sulfur dioxide, SO2, NOx, and then the PM 2.5 pollutants indicated that local mining operations emit approximately 50,000 kilograms per year of sulfur dioxide, 30,000 kilograms per year of NOx, and 10,000 kilograms per year of the PM 2.5. With average wind speeds of 4 meters per second, the simulation showed that pollutant concentrations are highest in the immediate vicinity of the mining sites, decreasing with distance. These findings suggest that while air quality near the mines is significantly impacted, the dispersion helps reduce concentrations over greater distances. However, areas within a few kilometers of the mines experience pollutant levels that could pose health risks, underscoring the need for improved emission control measures. For the water quality simulation, the average discharge rate of wastewater from mining operations was recorded at 5,000 meter cubes per day, with pollutant concentrations of 0.5 mg per liters for heavy metals and 50 mg per liters for total suspended solids, and 200 excuse me 200 mg per liter for chemical oxygen demand. Hydrological data, including a flow rate of 10 meter cube per second for the local river. Simulations conducted in MATLAB demonstrated that current wastewater management practices result in elevated levels of pollutants downstream, necessitating the implementation of advanced treatment technologies to safeguard water quality. So these are the graphs obtained from the simulation. The first one is on the heavy metals concentration in the river, the TSS concentration in river, and then the COD concentration in river. So the pollutant transport model highlighted the impact of mining wastewater on local water bodies. Discharge rate of 5,000 meter cube per day with pollutant concentrations of 0.5 for heavy metals, 50 for total suspended solids, and 200 for chemical oxygen demand was simulated against a river flow rate of 10 meter cube per second. The results show that the pollutant concentrations in the river are significantly elevated immediately downstream of the discharge point, with heavy metals, TSS, and cod levels exceeding safe thresholds for aquatic life. These findings emphasize the necessity for advanced wastewater treatment technologies to mitigate the adverse impacts on water quality. And the land degradation and reclamation simulation. Mining area spans 100 hectares, surrounded by 500 hectares of forest. The soil type in this region is sandy loam with an erosion rate of 0.1 tons per hectares per year. Reclamation practices such as revegetation and contour plowing were considered, with efficiencies of 80% and 70% respectively. So after the MATLAB simulations, this is the graph obtained. So the soil erosion model revealed the extent of land degradation due to mining activities and the effectiveness of reclamation practices. Without reclamation, the soil loss in the 100-hectare mining area was projected to reach significant levels over time, with an erosion rate of 0.1 ton per hectare per year. However, implementing reclamation practices such as revegetation and contour plowing, with efficiencies of 80 and 70% respectively, substantially reduced soil loss. The simulations demonstrated that revegetation is particularly effective, reducing soil loss by up to 80%, while contour plowing achieved a 70% reduction. These findings support the implementation of comprehensive reclamation strategies to restore land stability and prevent further degradation. So the next simulations were resource extraction process. Simulating the resource extraction process involves modeling various aspects of the mining operations, including the extraction rates, costs, environmental impacts, and economic outputs. After simulation, these results were obtained. So this is a graph for the cumulative profit over time, a graph for cumulative carbon dioxide emissions over time, cumulative water usage over time, and the cumulative land degradation over time. So the MATLAB simulations for Sudbury's resource extraction operations over a 10-year period reveal key insights into economic and environmental impacts. The cumulative profits reached approximately $2.1 billion, demonstrating strong economic viability driven by stable extraction rates and favorable market conditions. However, the simulations also highlight significant environmental concerns. Cumulative carbon dioxide emissions totaled around 255,000 kilograms. Water usage approached 445,000 meters cubed, and land degradation amounted to 0.6 hectares. These findings indicate that while the economic benefits are substantial, the environmental costs are considerable. Addressing these issues requires strategic interventions and sustainable practices to balance economic efficiency with environmental stewardship. And for the integration of renewable energy. To perform renewable energy integration simulations, especially in the context of a mining operation like in Sudbury, I considered various factors such as energy demand, renewable energy resources such as solar, wind, hydro, storage solutions, and grid integration. And after simulations, this is the graph obtained. So the simulation results for integrating renewable energy into Sudbury's mining operations reveal significant benefits. Over 10 years, daily energy demand ranged from 500 to 700 megawatt hour, solar energy averaging 4 kilowatts hour per meter square per day at 18% efficiency, and wind energy with an average speed of 5.5 meters per second at 30% efficiency provided substantial renewable energy with battery storage, balancing intermittent production. The renewable energy integration simulation showed that Sudbury's mining operations could significantly benefit from solar and wind energy. With proper investments in infrastructure and battery storage, reliance on grid energy could be reduced, which would lead to lower carbon dioxide emissions and enhanced sustainability. And this approach also aligns with global trends toward renewable energy and sustainability. And for the transportation network simulations, Transportation network simulations aim to model and analyze the flow of goods, services, and people within a transportation system. These simulations can help identify bottlenecks, optimize routes, and improve overall efficiency. So this is the graph obtained after simulation. Simulation of Sudbury's transportation network highlights the potential for optimizing logistics and reducing environmental impacts. The simulation identifies significant inefficiencies in the current track-based logistics. By transitioning to rail transport, which is more fuel efficient and has a lower emissions factor, the carbon dioxide emissions could be reduced by nearly half. Additionally, optimizing routes using advanced algorithms could further decrease travel distances and emissions, improving both environmental and economic outcomes. Water and waste management. Water and waste management simulations are crucial for understanding the environmental impact of mining operations and for developing strategies to mitigate these impacts. These simulations help in modeling the flow, usage, and treatment of water, as well as the generation, disposal, and treatment of waste. So, a graph obtained after simulations were performed. The simulation revealed that the daily water intake for mining operations 100,000 cubic meters sourced 70% from surface water and 30% from groundwater. The water is primarily used for processing, dust control, and other uses. And the simulation revealed that the current treatment facilities are inadequate to handle the full scope of mining activities. The untreated water discharge exceeds regulatory limits for heavy metals, including a need for upgraded treatment processes. By investing in advanced treatment technologies and increasing recycling, the environmental risks can be mitigated, ensuring more sustainable operations. Conclusion. Key insights. Long-term economic and environmental benefits outweigh the initial investment cost, making a strong case for sustainable development initiatives. Socio-economic strategies that promote local employment, community infrastructure, and transparent communication enhance community well-being and resilience. Strategic investments in infrastructure upgrades are necessary for sustainable resource extraction and have long-term economic benefits. Integrating renewable energy sources like solar, wind, and hydropower can lower reliance on fossil fuels and greenhouse gas emissions. Optimizing transportation logistics, including shifting to rail transport, can significantly reduce CO2 emissions and operational costs. And advanced water and waste management technologies are essential to meet environmental regulations and reduce contamination. And recommendations: implement advanced water treatment and cycling technologies to reduce environmental impact, invest in rail infrastructure and route optimization to improve transportation efficiency and reduce emissions, develop renewable energy projects to diversify energy sources to promote sustainability, allocate resources for necessary infrastructure upgrades to support sustainable practices, and our future work. Continuing to explore advanced simulation models for real-time monitoring and optimization, investigate additional technological innovations that can further improve economic efficiency and sustainability, foster collaborative approaches involving stakeholders to ensure holistic and inclusive development strategies. Thank you.